Okay, good afternoon, everyone. Welcome again. So today, this week, we have Caner Mercan is our speaker. Caner is joining us from Netherlands. Uh, Caner is currently a postdoctoral researcher in the computational pathology group of the Department of Pathology at Radboud University Medical Center, Nijmegen, since December 2018. After getting his bachelor's degree in computer engineering from Top Economics and Technology University in 2011, he received his master's degree in August 2014 and his PhD degree in 2019 with his PhD thesis on deep feature representations and multi-instance, multi-label learning of whole side, slide, breast histopathology images. From computer engineering department at Kent University. He is currently working on developing deep learning solutions to automate histologic grading of breast cancer and validate the prognostic value of the automated algorithms. His research interests include contrastive learning, graph convolutional networks, and multi-instance, multi-label learning. Thank you, Caner, joining us. So the scene is yours.
Thanks for having me. Hello, everyone, again. Today I will talk about AI-assisted histologic grading of breast cancer, with actually special emphasis on nuclear pleomorphism grading. But first, I would like to talk about the pathology workflow in a very shallow perspective. Well, I'm hoping that nobody actually knows much about the workflow in routine clinic, except if you know someone who's a healthcare worker, let's say. Here's a very broad depiction of what happens when a patient has symptoms and is subjected to screening. If the physician deems it necessary, a biopsy or resection is taken from the region in question, to be analyzed in the pathology department by the pathologists. Talking about these biopsies, here is a photo taken from the archive in the pathology department. In each row, there are hundreds of tissue blocks. Well, in the past, these tissue blocks, one can be seen in the bottom left. They were inspected under microscope, but with the use of whole slide scanners on the top left, the whole process is now digitized. On the right, you can see a digitized tissue block as a whole slide image, which is huge in size, and it's stored in multiple resolutions, as seen on the bottom right. Here's a nice demonstration of how large these images actually are. If you put a whole slide image next to a phone, which is a size about 15 centimeters to 7.5 centimeters, with 2200 by 1080 pixel resolution, you need about 22,800 of these phones stacked up against each other, like as you see in the middle picture. And on the right, there are some nice Dutch buildings to illustrate the size in real life. Well, as large as they are also quite time-consuming for the pathologists to also analyze and interpret and come up with diagnosis based on these interpretations. There are too many patients for too few pathologists. This shortcoming made headlines not too long ago in UK. It's arguably also very similar in many places in the world too. Pathologists are facing intense pressure from increasing workload. There's also an approaching retirement crisis, apparently, and the clinical services could be in jeopardy. So apparently there's some kind of need for automation. So enter computational pathology. It's comprised of digital pathology, medical image analysis, and machine learning. Well, nowadays only deep learning. We are at the heart of these three disciplines. Here in Radboud UMC, we are a group of people from different backgrounds working on various topics. Our group is in the Department of Pathology in Radboud UMC. We have 3 faculty members leading the research and 15 plus PhD candidates and postdoctoral researchers in the department. We have some technical staff to basically deal with the technical stuff, and a study manager for data management, student assistants for annotation tasks, as well as visiting researchers, currently mainly comprised of master's students. And it's also growing quite fast. In our group, we mostly integrate what exists in the deep learning domain into digital pathology from the perspective of medical image analysis. That being said, we publish in a very large spectrum from technical journals to medically oriented ones. Here are fairly two recent publications from our group with great contributions to their respective fields. One is from PAMI and the other one is the Lancet Oncology. After this brief introduction, I would like to talk about the main topic of this presentation. It's the breast cancer grading. There are three components in breast cancer to assess the aggressiveness of the tumor. According to a grading system from modified Bloom and Richardson, these components are scored into 3 points. The first one is the mitotic count. It's the number of mitotic figures per 10 high power fields in the microscope, basically. Or if you're looking at the whole slide images, it's just a small 2 millimeter squared region in the whole slide image. It is scored by the densest such region. So it's the hot spot of the mitotic figures detected or found in the whole slide image. So based on these thresholds, it's scored either as 1, 2, or 3 points. The second one is tubular formation. It is scored on the entire whole slide image, unlike mitotic count. It's based on the percentage of the glands. If there are glands that are normal looking, like the one on the left in the green, it gets a point of 1, and if it doesn't show any kind of normal appearing glands, it gets more severe points. And finally, nuclear pleomorphism. It is defined as the extent of abnormalities in the overall appearance of tumor nuclei compared to normal breast epithelium. So if it looks like normal cell, basically, in the breast epithelium, it's not as severe, but as you can see on the images, it gets quite aberrant towards the right. So after the points from each component are combined, the overall grade of the tumor is given. So if the grade, if the total is between 3 and 5 points, then the grade of the tumor is 1. It's kind of well differentiated and it's low grade, so it's not as severe. If it's 6 or 7, the total, then it's called grade 2 tumors. It's moderately differentiated and it's intermediate grade. And finally, of course, the most severe case, it's if the total is 8 or 9 points, then it's grade 3 tumors. It's poorly differentiated and it's high grade. So what we want to do is basically automate this breast cancer grading components, each of them separately. So how do we do that? We start with, of course, developing an AI system and then validate this AI system against pathologists. To see if it's performing as well as the mean or median pathologist or performing at the top level. And also then the next step would be to prove the added value of AI. So we just check or we need to show that it's actually improving the agreement between pathologists. That's quite crucial. If they use this, for example, system as a support decision system, if that's improving the concordance among pathologists, then of course it's an added value. The next step would be the large-scale validation of the prognostic value. But for this, of course, you need some kind of clinical data to know that if the patient survives, I don't know, some X years, Y years, and then you try to find a correlation between your method, the AI, and the survival of the patient. And hopefully at the last step, you redefine some of the rules that were set some decades ago and hopefully revolutionize the medicine. So far from our group, especially related to the mitotic count component, there have been multiple deep learning based solutions. For example, with this approach from TMI in 2018. Based on this work, we actually in our group proved that it's actually quite similar what the deep learning does compared to the manual counting by pathologists. As well as in another work based on, again, this method, we disproved, for example, one of the prognostic values, one of the molecular subtypes of breast cancer, which is called the triple negative breast cancer, and in which we disprove, for example, that mitotic count is not prognostic at all. So it doesn't have any say in the final survival of the patient. But today I will talk about my ongoing current work about automating nuclear pleomorphism scoring in breast cancer grading in much more greater detail. Let's remember how it was defined again based on the criteria. It gets a score of 1 if the tumor actually is bland and uniform, much like normal breast epithelium. It is a score of 2 for being moderately different, and a score of 3 in the presence of marked morphological changes, various other structures being more prevalent, like nucleoli in this case, in these images. But there is not, this is not really a quantitative method, right? It's more qualitative inspection. So where does exactly one score end and another one actually start? We don't really know. These question marks aren't really obvious. Maybe we argue in this work that they don't actually exist. Maybe it's more of a spectrum, because the pathologists, when they look at these images, of course, for them to be this granular, it's really difficult. But for the AI systems, it might be easier to find this, basically the spectrum as these continuous values. So without defining any discrete boundaries, suggesting 3 discrete grades, we propose to train a deep learning model considering the nuclear pleomorphism grading as a continuum of change in nuclear morphology or tumor morphology. That being said, this figure shows the overall view of the automated scoring of nuclear pleomorphism. First, invasive tumor in the whole slide image is segmented, which is important because these all 3 grading criteria, the components, they are only scored on the invasive tumor part of the whole slide image. And there are many, many more parts in the tissue which are basically diagnostically unrelated in this case. Then the pleomorphism in the tumor is scored as a full spectrum in the last part on the 3rd image, as you can see on the right. But before going into the details of the methodologies, I want to talk about the data sets. We conducted 2 different studies in this research. The first of which we call ARISE study. Here we selected 125 tumor regions from 39 whole slide images. And we built a web app and invited 10 pathologists from different parts of the world, score nuclear pleomorphism on the tumor ARISE. And on the right, you can see a query from the web app. On the left is a region with tumor, and next to it is a reference region for the pathologists to use as a baseline or a reference standard with normal cells. So based on this, they score the pleomorphism in the tumor. Following the guidelines, of course, we asked pathologists to score the pleomorphism into one of the 3 categories, 1 or 2 or 3. So overall, the study spanned 125 ARISE, scored by 10 pathologists from 6 countries, and it took almost 9 months from start to finish. And in the second study, it was designed to have pathologists score nuclear pleomorphism on the whole slide, on the entire whole slide images, instead of just selected regions of interest. For this, we collected an additional 118 slides and asked 4 pathologists from 4 countries to score them. Similar to the ARISE study, they scored pleomorphism into one of the 3 grades. Going back to the ARISE study a bit, I want to show the results or the feedback that we got from the pathologists. Here is the grade distribution. Each row actually corresponds to pathologists, and each column corresponds to a query like this one. And of course, the colors correspond to grade 1, grade 2, and grade 3 with green, yellow, and red, respectively. Actually, this figure portrays really well how different the scoring patterns of the pathologists are and how high the disagreement between the pathologists can be. Especially in the annotated region here, in these queries, some pathologists went for a score of 2, some said 1, some said 3, or given the score of 3 for the same tumor region. And again, these scores were assigned on homogeneous tumor regions of interest, not on entire whole slide images. on those entire whole slide images, the tumor morphology can be even more wildly heterogeneous, and resulting in even a higher disagreement between pathologists, basically. For these queries, we don't really have consensus grades, and as it's also visibly difficult to agree, as seen here. Therefore, we obtain the reference grades from the collective knowledge of these 10 pathologists. We can actually try majority voting. Well, majority voting suggests that the tumors in queries shown with arrows should be graded as 2, even though the distribution of the grades of the pathologists were kind of widely different. This is especially difficult because we would be telling, of course, the AI to treat the tumor in both regions equally, but there's a big difference. Therefore, we make kind of a bold choice because it's not done in clinical routine practice, but we treat this, the reference grade as the average grade of the pathologists instead of using some kind of majority voting scheme. This level of continuity is not usual in clinical setting, but of course it makes much more sense from a learning perspective. Effectively, of course, the setup changes a three-category classification problem into a regression task. And we can now have a look.
Excuse me.
Sure.
Can I have a question about the previous slide?
This one.
Here, the rows correspond to different pathologists.
Yes.
Is that correct?
Yes.
Okay.
Right.
And the columns are different queries.
Yes, exactly.
Okay. Okay, thank you.
Yeah, based on this. Yeah, in our methodology for learning to score nuclear pleomorphism, the first step was, of course, finding the tumor in the RIs. And we used an epithelial cell detector from a previous work of mine, which was utilized to detect tumor and normal cells in these RIs. Then we extract fixed size patches and sampling only from the areas with high tumor density. This is important, of course. We don't want we don't want AI to focus on regions without tumors, so that they would base their predictions based on some other factors in the tissue. And then the loss function here is, then the last step is the training of the pleomorphism network. It's a regression network again. Each training patch was associated with the average grade of the pathologists from the RI, which the patch is sampled from. Here the loss function is a smooth loss 1 between a prediction and the reference standard. And this setup is only aware of the cellular morphology of tumor, unlike pathologists who use also normal cells as comparison. So we wanted to test whether using the additional knowledge from the normal epithelium would be beneficial as well. So I sampled normal patches similar to how I do in B, based on the cellular density, basically. And then the feature embeddings of the normal patches are compared to the feature embeddings from the tumor patches. Basically, if the grade of the tumor is low, the loss is penalized less, but as the grade of the tumor increases, the loss is also penalized more severely. Here I use a tweaked version of the cosine similarity loss function. Here in the setup, both loss functions are intact. A through C learns grading, and it constrains the tumor to look more and more different from normal cells as the grade of the tumor increases through D and E. In our work, we used the RI study to train and validate the AI algorithm by the collective average knowledge of the pathologists, basically. It was also evaluated compared to the individual pathologists on a subset. On the other hand, the slide study was only used for the evaluation of the AI algorithm. Here is basically a breakdown of how we do this kind of data splits. Here are some results. Here there are 3 patches from the evaluation set in the RI study, with the AI predictions quantized into 3 categories, similar to the clinical setting in this case. Grades increasing from left to right. Hope it's visible on the screens. But that's not the only way the predictions by AI could be quantized, of course. With our methodology, we can choose to quantize the scores into arbitrary number of categories. Here are 5 example patches again from the evaluation set, with AI predictions quantized into 5 categories, increasing in grade from left to right. Of course, making correct predictions is important, but it's more important to show that it's making the predictions based on the correct reasoning. Here, there are 3 examples of correct predictions, and we used the GradCam to highlight the areas that played a great role in the predictions. In these examples, such areas are shown from yellow to orange to red with increasing impact. The areas with blue hues correspond to little to no impact. As you can see, the patches with correct predictions showed strong activation around nuclei. However, in few cases, such as the one here, the system overlooked the nuclear structures, basically, thus making a wrong prediction. However, this problem can be bypassed, as I saw, by processing multiple overlapping patches from the same area with small displacements and average pulling the predictions, basically. And because as the occurrence of this problem was few and far between, here I present the first quantitative results from the RI study on the 45 RIs. The AI predictions were quantized into 3 grades again, same as before, to be able to compare to the pathologists. On the figure, you can see the pairwise quadratic kappa scores between pathologists and AI. And here kappa means agreement, basically, the higher the better. The figure is sorted by the average scores, denoted by the large dots, with the highest being at the top. Each small dot corresponds to a comparison between scorers. In this case, it's either a pathologist or AI system. In this study, I achieved the highest average agreement score of 0.53. It also had the highest pairwise kappa score of 0.68 with pathologist number 9. While the results on those homogeneous regions of interests were impressive, we now consider the real-world scenario with slide level scoring. Same as before, the AI predictions were quantized into 3 categories. AI and the 4 participating pathologists were compared over 118 slides in the slide study. Here the results more or less depict a similar story, only this time around pathologist number 1 had the best average kappa score in this challenging task, and the AI was a close second. But the highest pairwise kappa score of 0.56 was between the AI and the pathologist number 1. I would like to emphasize the fact that the pathologist with the highest average kappa score agrees the most with AI, not the other 4 pathologists. Finally, here are some qualitative visual results from the predictions of AI on whole slide images. As seen from the color spectrum, there are different tumor regions predicted with different levels of nuclear pleomorphism. If we take a look at one of those regions with low-grade predictions, we see that the nuclei in this region are mostly uniform in size and shape, similar to normal epithelium in morphology. On another region with a relatively higher prediction, we observe that the nuclear morphology becomes irregular with visible nucleoli. Finally, on a region with more severe predictions, we observe that the nuclear morphology becomes quite aberrant with prominent nucleoli. Also, in the other test slides, we observe similar results, as you can see on 3 other whole slide images that further proved consistency. Here I selected 3 examples with mostly homogeneous pleomorphism across its tumor regions, increasing in grade from left to right, as evident from the colors from green to yellow to red. Of course, not everything is perfect. For example, here's a slide with multiple ductal carcinoma in situ regions. These are actually cancer as well, but it's not invasive cancer. And some regions with normal epithelium, which were actually predicted as invasive from the tumor detection algorithm. So it's the fault of tumor detector. And yeah, the pleomorphism network also scored it because it was detected as tumor. So this actually problem brings down the score of the slide. For example, this slide would be graded as something like 3 in the traditional 3 category classification. But because of this false predictions, it was graded as 2. And I saw this problem in just 2 slides out of the 118 slides. Which was like a big problem, that the overall grade of the slide actually was like 1 grade lower than how it was supposed to be. So even just correcting these 2 slides increased the kappa scores even more for AI. With this, I would like to conclude the presentation. Here are the main takeaways. We kind of showed that the AI could grasp the concept of nuclear pleomorphism scoring as a continuum of the change in tumor morphology. Training such a network did not need any manual annotations, which is one of the key limiting factors in computational pathology. And on top of that, AI performed up to par with the best performing pathologists in multiple settings. So full automation and validation of breast cancer components are halfway there, I think. We are getting there, and we are looking into a future with AI as an integral part of daily routine practice in pathology as well. And with this, I would like to thank everybody who has watched the presentation from the beginning to the end, and would like to have your questions if you have any.
Okay, thank you, Caner. Any questions from the audience?
I can ask one if there are no other. I'm assuming that there are other groups who are also working on this automated grading on digital pathology images. My first question is, how standard are these digital pathology images? Do they depend on the equipment that different groups have, or they are just standard? And second question is, are there any publicly available benchmarks on these data sets? Because further improving the models might be possible if there are publicly available benchmarks. Is that, do all the groups just create their own data sets and hide them, or release them?
Starting with the first question, it's definitely not completely standard, I'd say, because most of the different groups or even different hospitals use different whole slide image scanners, so they have different brands. And with each brand, there comes a different kind of something, and there is this called domain kind of transfer in medical imaging in this sense that you might do something well in just one domain or based on one whole slide image scanner, and then it might perform poorly on the other one. So that's also a problem that's seen in this field. But of course, you want to get as much data as you can, but like every other medical field, data is the most expensive part. Not really a lot of centers share their data. I mean, there's this whole slide images, and also there's this clinical data, which links the patients to the whole slide images, right? And you can get the whole slide images maybe, but you will never get the clinical data. It's really expensive, and they just treat it as like some kind of gold because it is really hard to collect. But in our case, what we do is just we have developed many different data augmentation techniques to deal with that. So in this, I didn't really go all the way in the details, but I use two different whole slides images from two different whole slide scanners, as well as I do quite heavy color and stain augmentations. On top of this whole slide scanners, there's also different staining techniques that you kind of color these whole slide images. There are so many layers to it actually, but yeah, I couldn't really fit all of it in this presentation. So yeah, there's definitely some kind of different domains, or let's say, whole slide scanners actually kind of result in different whole slide images, which might hinder the performance of AI. For the second question, I'm not really sure if I completely understood the question, because I'm kind of forgetting it. Can you repeat the question again?
Publicly available data sets, benchmarks.
Sure. Yeah, again, this kind of coincides with my first, I think, comments. It is quite expensive. We actually, in our group, we hosted some challenges in the past. And for example, with each organ, this grading criteria changes. It's not the same across all of the organs, all of the tissue types. So in this case, for example, I say that nuclear pleomorphism is very important for the prognostic of the patients, the survival of the patients. But let's say, I don't know, I'm just going to give an example. In prostate, I think, the tubular structures are the only structures that the pathologists look at. So nuclear pleomorphism is not even considered there. So that's just differences between different organs, I think. In terms of publicly available data, there are available data, but as I said in the presentation as well, creating a reference standard for these kind of components, it's quite challenging. In some cases, for example, in this chameleon challenge that we hosted on Kaggle, I think, and this year we hosted a panda challenge about prostate cancer. And I think in this panda challenge, they also provide some kind of labels for the grading of the prostate images. But I think also in our group we're the first ones to publicly to make these kind of data sets publicly available. But overall, I think it's quite still not there. Not every center or every group share their data. So it's really difficult to also judge or improve performance of the algorithms because of that.
Okay, thank you.
Any other questions? Maybe I can ask one. Thank you for the presentation again, Caner. So the colored query table with different gradings, I think that was really nice. This one. Actually, this is a very good example for one type of uncertainty that we utilize, aleatoric uncertainty. For each data point, we have the annotators provide conflicting labels.
Mm-hmm.
So have you thought about using that, or are people using this in the literature?
Not really. I didn't see much use case for that, actually. That's a good point. This was one of the first things that I tried, and since it worked so well compared to the pathologists, I didn't really go into the literature that much. But that's a good point that I can.
If this has not been used, I think this could be a really good point for using uncertainty, and it would be a good contribution. It really captures well the disagreement between in annotators. And you can the network can estimate the uncertainty itself as well. You don't need to provide a manual calculation.
Of course, using this kind of majority or average voting, you lose a lot of information. We knew that, but we just wanted to see if that made sense. But yeah, that's a great point.
Good. Any other questions, comments? Otherwise, we can switch to, we can stop recording and we can switch to the more fun part. So I'm trying to make it more exciting for people to join the live session and not watch the recordings. Okay, let me stop recording.